My talk today is about the selection of Meridiani Planum as a candidate landing site for the first crewed mission to Mars. In this talk, I will outline the priorities for such a mission, explore the exploration zone concept in terms of the type of region that a human mission would visit, outline the reasons why we chose Meridiani Planum, and then go through some of the criteria, the safety considerations, resource considerations, and science issues that help direct that choice. So in 2015, NASA held the first exploration zone workshop for human missions to Mars at the Johnson Space Center. And in this, the three key factors in deciding where to send people to Mars lay in the area of safety of the landing site, the availability of resources, particularly water, and the science goals of the mission and the ability of the site to meet them. In terms of safety, the baseline was the requirements for the Mars Science Laboratory mission, now the Curiosity mission, and the safety concerns were related to the landing sites and also to the hinterland surrounding the landing site, which would be explored by the crew. The water resources had to be sufficient to sustain the crew on the surface of Mars, ideally from the first mission onwards, but certainly for subsequent missions to the landing site. And lastly, the three primary science goals, which is why people want to go to Mars in the first place, consisted of astrobiology, atmospheric sciences, and the geosciences. So the exploration zone for a crewed mission to Mars is very different from the sort of regions that are explored during the Apollo program on the moon or by more recent robotic missions to Mars. The capabilities of a crewed mission are such that from that initial landing site, they may well be able to explore out to about 100 kilometers radius from that point, and thereby encompassing a number of regions of interest. This means that the landing site can be in the safest and most ideal site for landing, for establishment of the base, which usually means somewhere rather flat and boring, but much more interesting and perhaps more difficult sites can be then accessed from that in long-range excursions from the landing site. It's worth noting that these science regions of interest would each be equivalent roughly to the sort of area that is explored by advanced robotic missions, such as the Curiosity mission. And so you can see that within this 100-kilometer radius, you have the potential to achieve in a single crewed mission the equivalent of multiple robotic missions to the same area. And the resource regions of interest are places where resources such as water could be accessed to support the human mission on the surface of Mars. So why did we choose Meridiani? Meridiani was in fact a third round candidate for the Curiosity mission. It had all the engineering requirements. It was at a sufficiently low altitude. It was sufficiently low in latitude. The crosswinds and terrain, both smoothness and slope, all fell in within the parameters required for MSL class mission. And it was only dropped quite late in the selection process. Furthermore, Meridiani has a heritage of the Opportunity mission, which traversed more than 40 kilometers across the surface and provided a lot of data on both the scientific value of the region and also the operational issues associated with driving across the surface. And it was also selected from the candidate landing site for the Schiaparelli mission that unfortunately crashed on landing. So there's a lot of information available on this site, both from orbital data, site selection for actual landing, and from surface operations by the Opportunity rover. And here's the location on the equator, close to the prime meridian of Mars. The other sites were the other locations selected or documented at the workshop. And you can see that although there's a considerable number of them, almost 50, there's a cluster of them in the Meridiani region, showing that it is a region of significant scientific value, not just to us, but to other people looking at possible landing sites. Our exploration zone map shows there's a lot of sites, a lot of regions of interest within the 100-kilometer radius from the landing site, which coincides with that proposed for MSL back in the site selection days. These regions of interest are mostly both resource and science related. And so the Hesperian evaporites, for example, are both scientifically interesting and also a potential resource. And the same applies to the rampart craters, which may have subsurface ice associated with them. Then, of course, there's the Noachian bedrock to the south, and fluvial and inverted channels and Hesperian coastal sediments, all of which are of significant value to the mission. Beyond the 100-kilometer radius, there are a number of other sites which I've highlighted there, which could be accessed by follow-on missions. In terms of safety, this is what the ground looks like close to the landing site. It's very flat. There's firm substrate, bedrock at the surface, or with only patchy cover by a thin veneer of aeolian sands and gravel lag. These ripples are between 10 and 30 centimeters in height. And so there's relatively low risk of entrained debris during the landing process damaging a large crewed spacecraft descending to the Martian surface. The plains of Meridiani are very flat, and as the Opportunity rover showed, pose very little obstacle to long-range exploration. Despite the close horizon on Mars and the hazy atmosphere, visibility is usually very good. And here we have the rims of large craters visible to the Opportunity rover, even though they are 50 to 60 kilometers away. Navigation with a Mark I eyeball is no great problem. Unfortunately, the rover was not able to reach the uplands terrain to the south, but nonetheless, along the rim of Endeavour crater, a number of terrains similar to that encountered in the southern uplands were traversed by the rover. And in this image, we can see what that terrain looks like. It's undulating, it's not too steep, the going is firm, and there's not too much in the way of rocks. So no real obstacle is posed to exploration of this environment, either by rover or by pedestrian EVA to examine things such as rocky outcrops, such as seen here. The resources available are primarily water. Water for the manufacture of propellant, for the return journey, for exploration, and also water to support the life support requirements of the mission. The Burns Formation, which comprises up the plains at the landing site, consists of about 20 to 30% highly hydrated magnesium sulfate minerals. They contain 14 to over 60% water within the mineral structure. That means that these soft rocks, if they could be collected on heating, would yield about 10 to 20% water. In other words, a ton of this rock, which would occupy less than a cubic meter, would yield between 100 and 200 liters of water on heating to between 100 and 350 degrees. The other important regolith resource in the area is the sand and gravel, and also crushed rock. Regolith resources would be very valuable for covering habitats, for radiation shielding, should that be required, for the construction of berms, for protection of infrastructure from radiation from nuclear reactors, for example, or from debris from the landing and launch of Mars vehicles, and also for things like filling in holes and irregularities in the land around the Mars station to ease transport and driving around. And as this photo shows, on the edge of Victoria Crater, there's not only a surface veneer of sands, but in the ejecta blankets surrounding the craters, there's no shortage of blocks from gravel to quite large boulders available for use. The science targets in the area can be summed up by this image of the land terrain a little bit to the north of the actual exploration zone, where we have very well layered sediments of Noachian age exposed by erosion, and these sediments will provide records suitable to detailed exploration to uncover the astrobiological and climate history of Mars. Whether or not there are fossils in these sediments, we will not know until we go there, but certainly they'll contain a record of the habitability of the Martian environment and potentially preserve any biomarkers or even microfossils that would have been trapped as they're being deposited. From an atmospheric science point of view, there's a full diversity of processes evident at Meridiani. Large-scale processes such as regional clouds and dust storms are present. Mesoscale processes such as local winds associated with craters and valleys, and also the development and collapse of dust devils are evident in the rover imagery. And also we know that there are microatmospheric processes going on as well. Frosts and the transfer of volatiles between the regolith and the atmosphere and back again, as shown by the development of surface crusts along the surface of the plains. And here, for example, we have an image of a dust devil wandering its way across the floor of Endeavour crater. And the key to all of these things, as mentioned earlier, is the geological diversity, which allows any mission here to explore the entire geologic period on the surface of Mars from the early Noachian through to the present Amazonian. So in the southern areas, we have the uplands of Noachian rocks, exposures in the flanks of incised in paleovalleys, in crater rims. These are onlapped by younger Hesperian sediments, a mixture of evaporitic sediments, lacustrine sediments, old sand dunes, and perhaps marine sediments as well. These sediments are exposed again in craters, and they are fed by the paleovalleys mentioned earlier, draining down from the highlands, and also there are the preserved inverted paleovalley fills in the western part of the area, feeding into the area that was covered by the ancient depositional systems. And finally, the Amazonian period is represented by crater fills and also the surface veneers. And here we have some photos of the geology captured by the Opportunity rover. In the top left, we have the molds of evaporitic crystals and small hematite concretions about the size of peppercorns. In the top right, we have a gypsum vein through bedrock, a sign of a different kind of fluid process, groundwater circulating through the bedrock. In the bottom left-hand side, we have a vertically exaggerated image, a oblique image of the rim of Endeavour crater, and also a gully-like feature incised into it at some time in the past, possibly by water flow. And in the bottom right, we have ripples in the Hesperian sediments, indicating, again, water activity. So this is just a glimpse of the geological diversity discovered by the Opportunity rover, and there'll be a much richer suite of geological features open to a crewed mission, a crewed expedition to Meridiani that'll be able to cover a much greater area. So to conclude, the Meridiani Planum meets all of the requirements set up for the first landing sites on Mars. It meets the safety requirements. It has available water resources. and also it has significant scientific diversity in all the main fields to make the expedition there worthwhile. Now our study has been written up. Its references available there at the bottom, and download it and read it, and feel free to contact us with any questions. Thank you.